Okay, Dan, thank you for that introduction. Thank you for not attaching years to the when I acquired those degrees. Um, I hope we're not going to be interrupted. I'm in the business office in a hotel in Cape May, New Jersey, talking with the fishing community in terms of partnerships between using observations acquired by a fishing fleet in conjunction with models. So very much involved in what I'm going to talk to you today, and an important stakeholder group that looks at climate variability and climate change in coastal waters because of their impacts on fisheries. And just for context, the picture here in the background is Wildwood, just maybe 10 miles north of where I'm sitting. Nice sort of a beach area on the Jersey Shore. So as Dan said, I'm going to talk about work that my ocean modeling group, OMG, does at Rutgers for reanalysis. So coastal modeling, we, like in most data assimilation and state estimation problems, we want observations to use in conjunction with a model. And actually, by global standards, this is an extremely well observed coastal ocean. Still not as much as we would like, but what we have are sustained observations by the Northeast Nearicus and Mid-Atlantic Maricus regional associations of U.S. IUs. This sort of center picture gives you the scope of the general oceanography here for those people on the call who are not familiar with the Northeast U.S. There's relatively cool, relatively fresh water coming in from the north, from the Scotian Shelf, through the Gulf of Maine, and it heads southward down the Mid-Atlantic Bight, where it then departs from the shelf and mixes in this slope sea gyre that separates the Mid-Atlantic Bight Continental Shelf from the Gulf Stream itself. The Gulf Stream itself is not pushed up against the shelf, although it gets close to that at some times. And there's a set of other kind of novel observing systems. We've got tags on sea turtles, some other moorings, quite a large HF radar network, and of course the constellation of satellites. And one of the more novel things that I've been talking to people about today are these temperature probes. There's actually two here as an example of being intercalibrated, attached to the front doors of a trawler. And the map just shows the distribution of bottom temperature observations that we get from that trawl fleet. So sort of an exotic, unusual category of observations that are extremely valuable in this highly stratified environment. This is the framework, the modeling framework I'm working with. It's ROMS, Regional Ocean Modeling System, showing the domain here. The little green triangles are USGS river gauges, where we have river inflow. We force this with meteorology from the National Weather Service, and the open boundary conditions we actually take from the European Copernicus Mercator Ocean Analysis. We've made our own corrections to that for bias, and add tides and all of that. It's a roughly 7-kilometer resolution, 40 layers in the vertical. So data assimilation, I'm going to give us all a crash course on that. What we're doing in data assimilative state estimation is trying to come up with this analysis here, XA, right? That's going to be our best set estimate of the ocean. We start from a prior estimate, the background, XB, and in an operational forecast system that was just yesterday's forecast. And that's going to be informed by some observations. So if H is just, so I interpolate I sample my model ocean, XB, the background, in the same way as the observations here, Y. And so I just have a vector of model data misfits, right? That's the model error. Then I want to project that onto the model space, and that goes through this Kalman gain matrix. So this matrix has a number of rows that are the number of observations, a number of columns that are a number of variables in my model grid and time. So over 3 days in our domain, number of observations is about 300,000. If we consider the model state, it's 4 variables, right? Velocity components, temperature, salinity. There's about 1 million grid points. There's multiple time steps in the interval. That's roughly 9 billion elements, right? So this matrix K is 9 billion by 300,000, which is, bigger than the universe kind of thing, right? It's too many elements. We don't actually ever have that matrix. But we've got ways to get around that, to do this optimization problem, to figure out the best increment the K times the innovations to add to the background to improve the analysis. So what do I have? I have my ocean circulation model ROMs, just writing it here in the top line, putting everything on the left-hand side. I've got the time rate of change, the numerical, all the physics and the forcing, right? So that always equals 0 as the model equations are being calculated. And I want to optimize this fitting. So I've got two terms in this cost function that I'm going to fit, my cost function J. I've got the model interpolated to the observations, hx minus y, so that's the model data misfit. And I've got that transposed times itself, so that's just the sum of the squares of the element. That's the mean squared model misfit. And it's weighted by an inverse observation error. So if the observation is very accurate, O inverse is large, so that observation gets a significant weight. I've also got a background term here. So this is when I make my analysis, I don't want it to be too different from the original background. So I'm not going to make dramatic changes. Why not? You know, it might be that the observations actually are not that skillful, or they might have a large error in them. So I don't want to completely throw away the background. Plus, it's the background that carries the memory of all the previous observations that I've assimilated. So there's always a sort of a weighted least squares problem as I'm trading off the value of these two terms. So how do I minimize it? If you remember your Lagrange functions, right, I'm just going to take this model data misfit J, and then I'm going to add lambda here, 1 for every observation, times the ROMS model. So this term here is always 0, so I'm just adding a whole bunch of zeros, right? This is the magic of variational calculus. Why do we do that? Well, when I minimize this Lagrange function L, I will have minimized the model observation misfit while keeping faithful to the background. So minimize something, what do? You differentiate it by the variables that you have and you set the derivative to 0. So I differentiate this with respect to these lambdas, which I'll explain in a moment. Well, that's easy. All I get back is the ROMS model because this J doesn't depend on lambda. So that's saying that when I produce my analysis, the temperature and the velocity and the salinity will all be consistent with themselves according to the physics inside ROMS, right? So it's a dynamically and kinematically consistent state estimate. When I differentiate with respect to X, that's a bit more gnarly, right? Differentiating with respect to X up here in the J term, I've got something involving X times itself. I've got a half X squared. So when I differentiate it, I just get hx minus y times O inverse. When I differentiate in the nonlinear terms here, the ROMS part, that's a bit more complicated, but if you remember integration by parts, this might look familiar, is you end up with an equation that looks like this, which is these Lagrange parameters, the lambda I, which we call adjoint variables. It looks a lot like the ROMS model, but it's got a minus here. It's integrated backwards in time, and it's forced on the right-hand side by the model data misfits. So this tells us, going backwards in time, how that misfit in the model analysis projects onto the initial conditions of the analysis interval. And the other terms in here kind of connect it all together. So what we're essentially doing is I run a forecast if it's a real-time system, or my analysis based on my initial conditions at the start. Then I get some observations and they don't exactly fit the forecast. So I've got the misfits here, the forcing functions to my adjoint equation, the d lambda dt, goes backwards in time, right? Forced by those errors. So it goes backwards in time, and every time it hits one of these observations, gets a little nudge until I have my solution at time 0 for those adjoint variables. The other parts of the math connect those back to here to say how I should change that initial condition for the analysis. And when I make that change and redo it, hey presto, it fits the observations, right? So these observations have informed the initial conditions here to get a better analysis during this interval. We usually do 3 days. We also adjust the forcing conditions and the boundary conditions, but I won't go into those details. So that's the cycle we go through. Right. So we also use this analysis procedure to improve our mean climatology. I'm not going to dwell on that given the time constraints, but one of the things we do create is a mean dynamic topography, a mean sea surface height that we can add to the altimeter observations that we assimilate. And I just want to make the point that if you take the mean dynamic topography from Aviso, and this is people who work with altimeter data probably do that, this is what you're getting if you've got version 18. If you have version 13, 5 years ago, you got something like this. This is what our analysis looks like. And if you're a coastal oceanographer, this looks very convincing, right? We've got an across shelf pressure gradient that balances an along shelf geostrophic flow. I've got recirculation here around George's Bank. I've got a Gulf of Maine coastal current and outflow from the Scotian Shelf. If you take the mean dynamic topography from Aviso, it lacks many of those features. It's got these lines, which are basically streamlines of the geostrophic flow running into the coastline, all right? So this is why total dynamic topography from Aviso is a little bit unreliable in the continental shelf regions. But if you go through the procedures that we have, we can now use altimeter data all the way up to about the 10-meter isobath, or even shallower, right? Within 20 kilometers of the coast. So I'm going to skip over that too. So in our reanalysis, the observations we assimilate tabulated here. We've got infrared sea surface temperature from AVHRR, VIAs and GOES. We use microwave sea surface temperature at lower resolution where the infrared is unavailable. We've got sea surface height from all altimeter satellites on orbit, JSON, Altica, Crysat, Sentinels. Any in situ observations from NDBC buoys, Argo floats in our domain that go to the global telecommunications system, we harvest those. We've got surface velocities from a regional HF radar network. We've got gliders in the water. There's usually 1 or 2 in the water every month these days. And buoys in the Gulf of Maine and the previous OOI observations in the Pioneer Array in the Mid-Atlantic Bight. Details there about the error models we use. I won't go into that. We have a methodical procedure for evaluating our observation and background error models that involve these de Rosier statistics. I won't dwell on that either, but we do this posterior analysis to make sure our observation model is good. So how well do we do? What I'm comparing here is our assimilative Topio model, as I call it, analysis on the left, to what we started with on the boundary conditions, Mercator Ocean, the NRL's Global Ocean Forecast System, and our own model here on the right if we don't do any data assimilation. And so what we're seeing is, in terms of correlations and RMS errors, pale colors are good, right? A high correlation of 1 has a pale green, a very low RMS error of 0 would have a pale pink color. And so we see that overall our assimilative system has a better error performance than the boundary conditions that we used. So we have achieved added skill through the downscaling process and the data assimilation. And it's not just the downscaling, because our own model without assimilation is even less skillful than the Mercator Ocean system, which is assimilating data inside the domain. So downscaling helps, regional data assimilation helps. In terms of mesoscale, timescales of variability here, what I'm showing is a squared coherence in the frequency domain. So you want a coherence near 1. Our analysis is the blue line. We're better than all the other models across timescales from 1 day to 10 days to 100 days to interannual. And I've removed the seasonal cycle from this. So we're not just getting it because you're getting the seasonal cycle right. We're getting the mesoscale variability, the placements of Gulf Stream rings and meanders and filaments and coastal trap waves in the Gulf of Maine. So we've added significant skill across all time scales. So if you're interested in weekly to daily, weekly to monthly timescale inundation at the coast and sea level, this is good. I'm also going to skip over Taylor diagrams and say a little bit here about comparisons to bottom temperatures. So there's a program here called EMALT, Environmental Sensors on Lobster Traps. That's also EMALT, Environmental Sensors on Large Trawlers, and Environmental Sensors on Loggerhead Turtles. The EMALT program is giving us a bunch of this fisheries-related data. And again, light colors are good, small bias, small error, high correlation. Just looking at some very long time series stations through the Gulf of Maine and Mid-Atlantic Bight. So overall, okay, this study, this comparison is perhaps not as convincing as some of the others, but we have a tendency for lighter colored dots for our doppio analysis. So we're also improving bottom temperatures. We're not just getting the surface right because of those satellites. Now, just looking at temperature anomalies here for two time series. A couple of these time series are 20 years long. People have been going out and putting lobster traps at the same location through generations in their family, right? Fishing the same spot, giving us an incredibly valuable multiple decade subsurface temperature data set. And so we've got very good correspondence here between the observations and our doppio analysis at these individual temperature fluctuations. So warm years and cold years, warm months and cold months in the Gulf of Maine, we can use this analysis to inform some of those fisheries issues. And just something that has to jump out at you in that time series is the really strong warming trend in the Gulf of Maine. 1 degree Celsius per decade, right? It's 3 times faster than most other coastal regions. So the Gulf of Maine is really starting to cook. Discussions today, all sorts of issues about bacterial infections that are spreading northward at the rate of 50 kilometers a year. Infections in tautog and other fishes that you never would have seen in the New York area 20 years ago are now becoming commonplace. Again, a little bit more on the skill assessment. Scatter plot here with everything along the diagonal would be a perfect model. We can see this is before we assimilated these trawling data. So we've got less spread here in the doppio model compared to Mercator and to Goff's and to our non-assimilating model. Our next version of this reanalysis product, we will actually assimilate those observations fully, but they are in our real-time forecast system now for the observations that we get from the ships within 3 days, which is with most of them because they've got cellular comms on board the ships. And comparing to tags, these little tags here, they're glued on the back of a loggerhead turtle. I love that they're loggerhead turtles with data loggers on them. And you can see the wealth of data that we get. They're going down to 80 meters depth up in the estuaries, but all along the continental shelf of the Mid-Atlantic bight, giving us observations. And before we assimilate the data, we have this sort of skill. So we're right on the one-to-one line, right? There's no biases in here that have to be corrected for in order to use the mesoscale analysis that we have. We pretty much have an unbiased state estimate. And you can see by the colors here, these hits that turtles really love it when it's 21 degrees Celsius, right? That's where they're always hanging out. But those data are spread all over the shelf. We've also looked at some individual events, Gulf Stream rings and pushing into the Gulf of Maine. And now we're starting to use SMAP sea surface salinity data that we're forming the comparison here. We're having to, this is a busy slide about reconciling in situ observations from thermothermographs with the satellite salinity. And in fact, we're not yet there at the point where I'm confident to use these data on the continental shelf, but we're working on that. So the analysis that we've presented is described here. You can scan these QR codes if you want. The full reanalysis, 17 years of model output on the ROMS model grid every 1 hour. The 7 terabytes. It's accessible on our thread server. We are working at getting this into AWS Cloud now in a cloud performant format. There's a paper describing the reanalysis and progress in oceanography. And this link takes you to the data set URLs themselves. So if you want to actually work with this reanalysis product, that's where you go. And I think I'm going to stop there. We have an analysis of how these observations impact the model skill, which observations are the most impactful and least impactful. In a short take home, the value of in situ temperature and salinity data per datum far outweighs the information we get from satellites and especially from HF radars. So more observations in the water, subsurface, are what we need to improve the observation network for these reanalysis purposes, especially for getting bottom temperatures that are so vital to fisheries applications. And that's it. That's my summary of what we've accomplished. And I'm on my 20 minutes, so I'll throw it open to questions.
Excellent. Thank you so much, John.
Hi. You're downscaling global models. How do you choose what global models and how do you combine those and what, yeah.
Yep.
Yeah, I guess each of the many global models has different errors in different variables and so forth. How do you deal with that choice?
So our choice, we have limited our choice somewhat by the fact that we're also doing this for real-time operations. So we only really looked at global models that have a real-time delivery. So that's Mercator from Copernicus and HICOM model, right? GOFS, the Global Ocean Forecast System from NRL, are the two. I haven't looked at the Australian brand system, although I've been prompted to do that for some recent work by others. What we did is we evaluated those compared to our suite of observations inside our domain, which is quite dense. And I know a lot of those observations are not assimilated, or previously were not assimilated operationally by, especially by Copernicus. That's the system I know best. I presented a talk when I was on sabbatical in Toulouse in 2018, and I showed them how much data we have that they are not assimilating. And then I went back and tried to make the same plot 18 months later, and they had assimilated all those data. All right, so Mercator are really on it. And actually, if we went through this in detail, the Mercator Ocean product is consistently more skillful than the Navy HICOM. So the choice has become easy for us. We use Mercator, but we have our own data assimilative climatology. So we have compared a climatology of Mercator to ours, and we subtract out their long-term 20-year mean and replace it with ours, retaining mesoscale variability, but correcting for biases.
Wait, sorry, you went so fast at the very end. Can you say that again? Is that the main difference between, I guess, the French, what the French are doing and you are doing?
Well, we have so we have bias corrected the mean in Mercator. Now we did that with a climatology that we computed based on 20 years of hydrographic data in our region. And given the trends, the warming trends in this region, I think we probably should go back and revisit that, because what we thought was a warm bias, a somewhat warm bias and salty bias in Mercator may not be as much of a bias as we thought it was, because the ocean has warmed up so much in those 20 years. Yeah, 2 degrees in the Gulf of Maine. It's pretty significant warming trend. So we need to do that a bit more carefully. And I think Mercator has improved so much in the 10 years that we've been doing this that I'm prepared to accept it as it is for our next version of this, which is extending. The model we're building now goes from the Grand Banks to the mouth of the Orinoco River. We're applying the same methodology in a mixed resolution assimilation system for the East Coast.
Thank you. I see Jimbo.
Yeah, Jimbo, go ahead.
Yeah,
Can I
thanks.
hear you? Okay.
Hey, 你在我做video 里面 Seriously. Sorry. Yeah, I think okay. I can go first, and I think Dimitri is before me. Hey, John, thanks for joining us, and thanks for a wonderful overview. Two questions. One is, there are so many machine learning talks, and do you see any new kind of type of machine learning that incorporate into your system? The second question is, SWOT is coming out now with the super high resolution information. How do you plan to incorporate this high resolution, spatial resolution information, but sparse in time?
Okay, that's a lot, Jimbo. Machine learning, I think there's a lot that can be done in analyzing this analysis to understand some of the modes of variability in there. So from a 20-year reanalysis, There are things we could look at, like, the occurrence of Gulf Stream ring intrusions. Is the frequency of that changing? What does an event like that do in terms of bottom temperature changes or something, right? Something where we could connect a very observable phenomenon, like a sea surface height anomaly, SWOT, with subsequent changes in the marine environment that are obscured to us from our satellite view. So using the model to extrapolate, project into the subsurface. So there's that sort of thing. In terms of the analysis system itself, we have not been involved in this, but I have other colleagues in the data assimilation world that are finding that one of the potential areas there is to have a more objective assessment of the background error, right? The background error is basically what are the inherent errors in the model? And that's a very hard thing to get down to, right? Because you've coded this model as best you can. I'm not really sure what the sources of errors are, but a machine learning approach, may be helpful in bringing some more nuance to that background error. So I'll leave the machine learning thing at that. With any altimeter data in a high resolution coastal model, it's a difficult challenge in that we've got lots of high frequency sea level signals that most altimetrists try to remove, right? You take out the tides, you take out the inverse barometer, you take out the high frequency coastal trap waves. And that's all physics that's important for us. We don't take that out of the model. So we tend to put that back into the altimetry. And I understand why the altimeter community does that, because you really, in order to combine the conventional nadir altimeter constellation into a map, you're saying, let's get the observation down to a mesoscale, sea surface height variability. Then we know what length scales and time scales to map that to produce a sea surface height analysis on the 10 to 15 day time scale. Great. So when SWOT comes along, what do? We've got this fantastic spatial resolution, but I've only got it every 5-7 days, maybe, at this latitude. And so there's a mismatch there between the time and space scales. So where we are taking it is getting a more sophisticated observation operator, where we actually go back and start doing things the way conventional altimeter scientists do, and just reducing the observations to that mesoscale, or maybe even sub-mesoscale sea surface balanced variability, perhaps. And we need an observation operator in the ROMS model that therefore filters over time the same way that you're pre-processing the altimeter data. So that's what we're doing. It involves having an extended time period of forcing in the adjoint equation, but we know how to do it. We're going to try that first.
Thanks, John.
All right, I think we have time for one more question. Dimitri, go ahead.
Hi, John. Thank you for the presentation. Very interesting. I have a question about altimetry assimilation. What method do you use? Because there are different techniques that could be applied to assimilate SSH and project the information into the subsurface layers. Is it like Cooper-Hens technique or something else? And another small question. So I noticed that you use SSH anomalies, and so I have experience working with RTOS, which is something similar to GAVs, but we use different techniques for SSH assimilation. And we had a lot of problems trying to assimilate SSH anomaly related to big uncertainty in the mean MDT field. So we had a better success with using ADT SSH, absolute dynamic topography. So if you could comment on this as well, it would be great. Thank you.
Yeah. Okay. So I guess I muddled things there a little bit. We do assimilate absolute dynamic topography.
Oh, okay.
That's the state variable in ROMS, and that is how we pre-process our altimeter data.
Mm-hmm.
But maybe I skimmed over it quickly. But we have our own mean dynamic topography here.
Mm-hmm.
That is based on a climatological long time scale 40-var analysis of climatological data in our region. And that's why we have this more realistic version of the MDT against the coast compared to a VISO up here in the left. So yeah, if we use this mean dynamic topography and added altimeter heights to it, we would screw up our coastal currents in the Gulf of Maine, for sure. But we have a dynamically consistent, because it's gone through the ROMS 40 VAR, so the velocities in the sea level and the geopotential anomalies are all dynamically consistent, so that we can take conventionally processed sea surface height anomalies. That's how we get around our geoid problem, right? Which is a real problem in the coastal zone because of the short length scales. And that gives us a much better absolute dynamic topography estimate than we would get if we took the Aviso MDT. Now, how that projects onto everything else is through the magic of the variation analysis, and it's the adjoint. All right. So our salinity, sea surface height observation is part of the state variable of the observation vector y. We sample the model at that point. It's got the same physics. We've got inverse barometer dynamics in both the altimeter observation. We've put the tides back in there. All that variability is there. So our hope is any mismatch between the altimeter observed sea level and the model is due to the slowly varying part of that. This projects onto, this is the whole state variable, right? There's an adjoint variable for everything. So an anomaly in sea surface height projects onto temperature, salinity, velocity in a dynamically consistent way because the adjoint equation is the same physics. It's linearized about a background state, but it's the same physics as the hydrostatic primitive equations. So we're relying on, this is our covariance, if you like. This is where the Cooper-Haines stuff is. It's coming out of the adjoint equation.
Thank you.
All right, well, that's all the time we have. So let's please thank John again for a really nice presentation and discussion. And please join us next month for the next installment. We'll be joined by Dimitri from NASA JPL Mendemenlis. He'll be discussing a global high-resolution coupled air sea modeling. So thanks again, John.
Right.
Thanks,
Thank you.
John.